Hi everyone, my name is Taehyung from KAIST in South Korea. I'm presenting our work about SliceNStitch, continuous CP decomposition of sparse tensor strings. Tensors are multi-dimensional arrays that are powerful tools for representing time-evolving multi-aspect data. A multi-aspect data stream is a sequence of time-stamped m-tuple consists of non-time mode coordinates, value of the event, and the timestamp when the event occurred. They can be found in many different areas, including traffic history, crime history, and purchase history data. For analyzing the tensor, CP decomposition is widely used. CPD gives a low-rank approximation of the tensor. Using CPD, tensor X can be approximated as X tilde, the summation of outer products of vectors, and these vectors form the columns of vector matrices. Therefore, the goal of CPD is to find vector matrices that minimize the difference between X and X tilde. While tensors and CPD are powerful tools, their common modelings have a serious limitation for time-evolving data. This is because there is a mismatch between the input data stream and the tensor, which is that dynamic tensor grows only once per period, while the input data stream grows continuously. Therefore, outputs of CPD are also only updated once per period. To perform CPD continuously for real-time application, one can make the granularity of the time mode extremely fine. For example, right fine-grained tensor can be updated more frequently, once per second compared to the left coarse-grained tensor, which is updated once per hour. However, the CPD with fine-grained tensor causes the two main problems. First of all, it causes the degradation of fitness. An extremely fine-grained time mode results in an extremely sparse tensor, which is known to be of high rank, and thus it degrades the fitness. Second, it increases the number of parameters. An extremely fine-grained time mode leads to an extremely long time mode, and thus extremely many parameters. Therefore, the common tensor modeling with fine-grained tensor is not suitable for real-time application. Then our problem is, how can we continuously analyze multi-aspect data streams using CPD? More specifically, given a multi-aspect data stream, how to update its CPD instantly in response to each new tuple in the stream, without having to wait for the current period to end. In this research, we proposed the new continuous tensor model and its efficient implementation to answer this question. In our new continuous tensor model, the time range of the tensor window and units changed adaptively at each time. In this example, the tensor unit which aggregates the event from 2 o'clock to 3 o'clock is updated to aggregate the tuple from 2 o'clock 1 second to 3 o'clock 1 second, when the current time changes to 3 o'clock 1 second. In the continuous tensor model, it is crucial to efficiently update the model's tensor. Therefore, we propose an efficient event-driven implementation of the continuous tensor model. Assuming a single time-stamped tuple with the value v, then it generates an event that moves v from one unit to another. We can simply implement it by subtracting v from the source entry in the previous tensor unit and adding it to the destination entry in the new tensor unit. Let's look at how SliceNStitch updates the tensor decomposition based on the continuous tensor model. The first one is SliceNStitch matrix. Given a high-order tensor, CPD yields a vector matrix for each mode. This method updates all entries in the matrix at once by solving the least square problem. Note that SliceNStitch matrix uses all non-zero entries in the tensor for all updates. Thus, it acquires a high-quality solution at the expense of high computational cost. We invent other approaches to reduce the computational cost, and these are the outlines of them. Remember the case where the values of the tensor are changed by the event. So it makes sense to only update rows corresponding to the changed tensor units. In the case of non-time mode, given two entries altered by the event, one can extract a single slice that includes those entries. Updating a single row of the vector matrix that contributes to feeding that slice may be enough for obtaining a nice solution. With these backgrounds, I'll introduce our second method, SliceNStitch vector. For the time mode, we use x tilde instead of real tensor and solve the least square problem. This allows us to finish the computation in time proportional to the number of non-zeros in X, which only has 2 non-zeros. For non-time modes, we solve the least square problem with respect to only a single row, which is used to fit the slice changed by the current event. Time complexity is proportional to the number of non-zeros in the slice. SliceNStitch vector is significantly faster than SliceNStitch matrix, but it's numerically unstable and slows down if many non-zeros are of the same index. The next method, SliceNStitch random, has two different behaviors. Given a threshold setup, when the number of non-zeros in the target slice is smaller than setup, we solve the original least square problem. If the number of non-zero is larger than setup, the original tensor is approximated to x tilde. Then, we randomly choose zeta indices from the target slice and correct values of these entries as real x. This allows time complexity to be proportional to zeta. The advantage of SliceNStitch random is that it finished in constant time. However, it is numerically unstable, and its accuracy is worse than that of SliceNStitch vector. Our final method is SliceNStitch stable. SliceNStitch vector and SliceNStitch random are unstable because many products are required. This makes two large numbers that hinder the accurate calculation. Unlike the previous method, SliceNStitch stable update row entries one by one, and click the updated values if it is too large. This method guarantees to not increase the objective function, although it is clipped. Before checking the experiment results, let me introduce the experiment settings. We use 4 real-world tensors from traffic and crime domains. 4 baselines that periodically update CPD are used. This slide shows how the accuracy of our methods and baselines change over time. We use the relative meanness, which is the higher, the better, for the accuracy measure. There are 2 kinds of any CPD according to the iteration number. Performances of baselines are revealed per update period, while that of our methods are revealed every time. As you can see, our methods work similarly or better than baselines, and this holds for all datasets. Note that performances of SliceNStitch vector and SliceNStitch random suddenly dropped in Chicago crimes and Wright Austin datasets due to their instability. On average, our bestest method, SliceNStitch random plus, shows at least 72% of relative fitness to the most accurate baseline, ALS. In addition, our most accurate method, SliceNStitch matrix, nearly shows the same fitness compared to ALS. All versions of SliceNStitch update vector matrices significantly faster than the fastest baseline, CP3. Especially, SliceNStitch Random Plus is up to 464 times faster than the fastest baseline. SliceNStitch is scalable with respect to the number of events. That is, its running time is linear to the number of events. Remark that sampling threshold zeta is required for SliceNStitch random. As zeta increases, the fitness increases with diminishing returns. But the increased zeta linearly increases the runtime. In the case of clipping threshold for SliceNStitch stable, it is okay as long as the threshold is small enough. You can see that the performance dropped in Chicago crime when you use a too large threshold. For users of our method, we do not recommend SliceNStitch vector and SliceNStitch random due to numerical errors. We recommend using the most accurate version within your runtime budget, since there is a trade-off between time and performance among our methods. If SliceNStitch Random Plus is chosen, increase zeta enough within your runtime budget. To conclude our research, optimizing a continuous tensor model with SliceNStitch achieved your instant updates, high fitness, and a small number of parameters. This is the end of our presentation. Thank you for listening.